Every time we open a language model, we start from scratch. No matter how many times we've explained something before, each interaction is independent, as if it doesn't know us. This isn't just a random bug, but a direct consequence of how they're designed. They train once for months on massive amounts of data and then remain frozen. They don't incorporate anything from our daily interactions with them. Meanwhile, we're seeing that making them larger no longer yields dramatic quality improvement. Costs rise significantly while improvements become increasingly marginal. So the problem is twofold. On one hand, models don't learn from experience, and on the other, their bigger is better approach is showing its limits. We need another strategy, or rather, several. We can imagine AI as a brilliant student with terrible memory. Every day it wakes up without remembering which exercises it did well, which ones confused it, or which explanations helped most. Each test is like taking the very first exam of its life. That's essentially what happens with many current models and the agents we build on them. They approach each task as if brand new, without leveraging past experience. In response, we now have two main approaches changing the landscape, one from Google, another from MIT, plus an intensive practice concept that enhances them even further. We can view these as complementary ways to help that student, providing a well-organized notebook and allowing them to rewire their brain so certain lessons become automatic. The first approach is Google's, and it's called Reasoning Bank. We can think of it as an external notebook where people not only record what happens but transform it into general strategies. And the crucial thing here is that it doesn't just stick with what worked well, but also learns from its mistakes. A failure stops being noise and becomes a useful warning and something not to repeat. The cycle works like this. Facing a new task, the agent checks its memory and retrieves relevant lessons. It acts with that guidance. Afterward, a model evaluates the result, whether successful or not, and new memory items are distilled from that experience. Each one has a title summarizing the idea, a description of when to use it, and content with refined steps. It doesn't store specific clicks or complete paths, but strategy patterns that can be reused in completely different websites or environments. The quantitative results are promising in environments like Web Arena. An agent without memory achieves only about 40 to 47% success, and when we incorporate the reasoning bank, the success rate rises to about half of the tasks solved, with increases of over 8 percentage points in some scenarios, plus a reduction in steps by about 16%. It not only gets more correct answers, but reaches solutions faster, avoiding unnecessary detours. On this foundation emerges another key piece: intensified practice, guided intensive training, known as MAP. The idea is giving AI more opportunities to practice the same task before delivering the final result. What's interesting is how the circle closes. A good memory ensures this practice isn't blind, but directed towards strategies that have already proven promising, and that practice produces higher quality experiences that further enrich the memory. Better memory leads to better practice, and better practice builds an even more useful memory. The second approach is from MIT, which is more radical, called SEAL, or Self-Editing Language Models, which are self-learning models. Instead of just using external memory, the model learns to rewrite its own parameters with the goal of generating its own training examples and update instructions. The SEAL cycle works like this. We give new information to the model and it proposes a self-edit, essentially a study plan for integrating that information. It applies this plan through a small fine-tuning process on itself and then evaluates whether it has improved or worsened. Based on the result, it reinforces or penalizes that type of self-editing and over time discovers which training procedures work best. The numbers show a significant jump in tasks like squad. Accuracy increases from 1/3 to almost half. In a comprehensive benchmark of abstract reasoning where the original approach with standard in-context learning achieved 0% success, the complete SEAL version has reached over 70%. Reasoning Bank has its own risks, primarily depending on the quality of stored memories. If an agent distills an incorrect strategy, that flawed lesson can spread to many future tasks. Additionally, proper memory index management is crucial to find relevant information, and the context window limits how these instructions can be injected. This adds to a shared challenge of interpretability in Reasoning Bank. At least the memories exist in natural language, allowing us to track what has been learned. ChatGPT's brain has just been changed, and although it seems like just version 5.1, the difference is extremely noticeable. This isn't a simple touch-up. Now the model is smarter, more conversational, and above all, much more customizable. Let's see what this update really brings, how the new modes work, and how it handles instruction. So let's start with the basics. When we open ChatGPT now, we see three options under the same 5.1 model: automatic, instant, and thinking. The automatic mode chooses for us and switches between instant and thinking. Instant is the fast one, used 90% of the time. It's warmer, more direct, and follows instructions much better than previous versions. It incorporates ADA adaptive reasoning and answers simple questions immediately without complications. Thinking is the reasoner. It's designed for problems requiring deep reasoning, advanced math, complex code analysis, logic, business strategy, or any task where reasoning quality matters more than speed. With instant, we see it clearly, and thinking appears when we have significant doubts or are asking about more complex problems like logic puzzles, code, and so on. Beyond reasoning, one of the major innovations is how it converses and follows our instructions. You can tell the model has been refined to communicate better with people. Now, when addressing, if we ask it to speak to a 70-year-old, the model adapts its language to be simple, relatable, and understandable, using clear comparisons without unnecessary technical terms. But if we ask it to explain that same concept to someone with a doctoral degree, and it can respect both technical language and formatting, which wasn't possible before. Previously, it ignored these details, but now it better respects the type of response we request. It's also more rigorous when we set restrictions, something older models struggled with more. The other major feature of this version is style and tone customization. From the settings menu, we can activate personalization and select a base style. There we find several pre-designed personalities like professional, friendly, sincere, peculiar, efficient, geeky, clinical, or even cynical. When we activate the professional style and ask questions like, why should we learn to use AI? The response is organized, formal, with well-structured arguments, relevant data, and a tone fitting for a work presentation or serious report. If we switch to a clinical style, the response pattern changes completely. It keeps the accuracy, but the tone can be drier or more ironic depending on the example, with a very specific humor. We haven't seen this prominently before. Then we have geek mode, where the tone shifts again. Responses include references, naturally used technical terms, and a more casual, friendly tone, like talking with someone deep into the tech or gaming world. This customization isn't just cosmetic, it also affects practical tasks with professional personality. For example, we can request an email reply to a price reduction request, and the result is typically polite, firm, and concise, maintaining position without sounding aggressive. If we combine thinking mode with a geeky personality, that mix works extremely well for programming. The update is noticeable not just in what the model can do, but in how it accompanies us while we work. One way to leverage it is using the desktop app to keep it alongside whatever you're working on. So basically, with version 5.1, we've moved from just having a powerful model to something more adaptable. It follows instructions better, adjusts task difficulty, communicates more naturally, and lets us customize the tone to match our style or the situation. Now it's our turn to experiment with instant and thinking modes, play with different personalities, use it as a co-pilot alongside our apps, and see where it can improve our daily workflow. So basically, we want to start incorporating these functions into our workflow and try reasoning challenges, create small tools with code, draft important messages with the appropriate style, and especially observe how the experience changes when switching modes or personalities. This way, we'll truly understand what this new model offers and how we can best leverage it in each situation. So anyway, tell me what you think about these changes if you've tried it already. I've tried it myself, and I have to say that the method, or rather the thinking section, is vastly superior to the previous one. So yeah, having a model that takes 4 or 5 minutes to give you an answer, but gives you a perfect one, is definitely what matters most. Alright, let's talk about something that, in Google DeepMind's own words, is a significant step toward artificial general intelligence. We're referring to SIMA 2, the new AI agent that thinks, acts, and learns in 3D worlds, and can improve on its own without constant correction. What is SIMA 2 and why does it matter? SIMA stands for Scalable Instructable Multi-World Agent, a scalable, teachable agent designed to operate across multiple worlds. The first version of SIMA was the first serious attempt to convert natural language instructions into actions within video games and 3D environments. SIMA 1 could follow basic commands, turn, climb ladders, open maps, but it didn't go much beyond that. It didn't seem to truly understand what it was doing, but with SIMA 2, the story changes. Now people can reason about their goals, talk to us, explain what they're trying to achieve, and most strikingly, improve themselves over time without direct human intervention. All this happens because SIMA 2 integrates Google's most advanced Gemini models, which act as its reasoning and feedback brain. In this new version, SIMA 2 isn't just executing commands, it interprets our goals, breaks them into steps, chooses actions in the 3D world, and explains what it's doing and why. Google describes it as an interactive gaming companion, not a clumsy bot that just obeys, but an agent that understands context, evaluates options, and makes decisions. Additionally, thanks to Gemini, it greatly improves generalization capability and reliability. It understands much more complex and nuanced instructions and completes them even in games it was never trained on. This is key when discussing more general artificial intelligence. It's not about excelling at one task, but adapting to many different situations. Looking at the data, the leap is enormous. In evaluation tasks within 3D environments, SIMA 1 had a success rate of about 31%, while SIMA 2 reaches 65%. The human benchmark is around 75%. This means SIMA 2 is just a few points behind an average human player in these specific tasks, and impressively, this improvement came in just one generation of development. In previously unseen environments, SIMA 2 consistently outperforms SIMA 1 by a wide margin. It generalizes better, completes more tasks, and navigates new worlds much more effectively. One of SIMA 2's most important capabilities is that it doesn't just memorize, it can learn new concepts and reuse them. Additionally, the next step is even more striking, combining SIMA 2 with Genie 3.0. Genie 3.0 is a world model that generates interactive 3D environments from a single image or text prompt and maintains consistency for several minutes. We can navigate this world, modify it, and the system remembers what happened. It has environmental memory. When SIMA 2 is placed in these newly created worlds, something powerful happens. People have never seen these environments before. Yet it manages to orient itself, understand our instructions, and take reasonable actions to achieve objectives. In other words, we have a model that generates worlds and an agent that acts within them. And Gemini, providing vision and reasoning capabilities, is an AI agent playing, exploring, and learning inside a world that doesn't exist. Furthermore, what makes SIMA 2 especially interesting is its capacity for self-improvement, and it has an initial phase with humans, then a self-learning transition, and finally uses Gemini as an internal coach. Its own experiences become training data, with every attempt, success, and error saved as experience. Although SIMA 2 currently exists in virtual worlds, the implications extend far beyond gaming. In the real world, robots need to understand physical spaces, navigate changing environments, manipulate objects, follow instructions, and maintain goals through multiple steps, similar to what SIMA 2 practices in these 3D worlds. The idea is to train most of these skills in simulations and AI-generated worlds that are safe, inexpensive, and virtually unlimited in variety. Current limitations for AGI mean it's far from perfect, still makes mistakes, has limited long-term memory, and sometimes shows incoherence and strange environmental changes in generated videos. Even so, its combined capabilities are what transforms it into something truly significant. We're not at AGI yet, but looking at the leap from SIMA 1 to SIMA 2, from an agent barely completing simple tasks to one approaching human-level performance in many cases, generalizing better and training itself in generated worlds, we see key pieces coming together incredibly quickly. If this pace continues in future versions, we're likely approaching general autonomous systems capable of functioning in both virtual and real worlds much faster than many anticipated.